Hey everyone, we'll go ahead and get started here. How is everybody doing? We're on the ultra low latency, which is amazing. I love that 3-second delay. Hey, what's up, Jake? Do you have some questions? I'll pull up the 474. If you have questions, we can start talking over the work. Feel free to ask. You're here, you get the questions to go first. So let me get 474 up and going. Let's see. It's always, I always download a fresh copy of the assignment when I get started. So let's go to predictive analytics, linear regression. Be good for 320 to hear in on this stuff too. Okay, I'm getting the data loaded up. Is Mubot? Mubot's awake. Wait, let me reset Mubot. Mubot needs to be reset. Mubot, wake up, Mubot. Arise, Mubot. Come to life. Mubot is waking up. Could you talk a little bit about question 3? Yeah, and I think we have that one labeled properly. Question number 3. Is it the interpretation of coefficients? Is that the one you're talking about here, Jake? Mubot is awake. Let's go over here and let's look at some interpretation of coefficients. Class is over. No. I should take that down sometimes. Are you talking about this one right here, the interpretation of coefficients? Is this the one? Is this the question, interpretation of coefficients? Aha, good. So using the LM function, not trained from caret, we'll be using trained from caret very soon here, create a model. And so we need to use the LM. I was doing this a little bit in class today here. I was creating LMs. GLM is the generalized linear model. LM is the linear model. And so we want to make a model. It's down there, cool. We'll go right here. We're gonna insert a chunk. You can always insert a chunk when you want. I'm just going to call this Q3 new chunk. You can just call whatever you want. You can do the chunk down lower. I just emailed you about, yeah, what is the question? Okay, yeah, Jordan, you got it. We were just emailing about that. I emailed you just back about it, I think. I'll do that here next. You got it. We're going to do some interpretations of coefficients. And then question 3 on chapter 14. You were asking about the 1.645. What's up, Mohammed? So good to see you here. Love it. Everybody's here. Happy day. We've got the value. Don't I have value in here? There we go, value. This is already a data set that exists in here. So we can see all the value right there. Fit a multiple regression predicting customer lifetime value from all the variables, I believe. Yep, on the entirety of the data set. So let's go here to M, save into LM, customer lifetime value, ~. This stands for, hey, what's up, Amber? So good to see you here. Yep, and I think you were asking on Discord, so you were asking about the overfitting, right? I think you figured it out, right? One person asked, and another person figured it out. So we can talk about the overfitting right here, because I think we show that graphic. So good to see everybody here. Yep. And we'll talk about the overfitting here. So we can do that. We'll talk the 474 stuff right now. Then I'll hop over to tool 1 here in a moment. This is the fitting of the quantitative model. This is not logistic because it's a quantitative model. We talked about logistic in class today. We'll be talking about this in 320 very soon. Logistic is the sigmoidal curve. We're not doing logistic regression. There's a difference in the code. I'll show both at the same time. The code for logistic has to use the GLM, which is a generalized linear model, and it uses the binomial, which means we have like yes, no's. Don't include this, obviously, but I'm just trying to show the difference here between linear and logistic. So here's the key difference. Yeah, of course, Mohammed, feel free to ask it. We'll definitely do it. We got tons of time. We just started. Everyone's here, though. I love it. So this is good, Mohammed, too, right here to see the difference between, you'll be covering this very soon. It'll be one of our last chapters in the class, but the difference between linear and logistic. And you see that linear has LM, Y tilde X, comma, data equals, and logistic has GLM, Y tilde X, comma, data equals, comma, family equals. What's up, Miles? So good to see you here. Man, such good office hours. Love it. Well, guess what? I bet some 320 can help out with this because we're going to make a summary of this model right here. And we've got transactions as the first variable we're going to start interpreting. So if you notice here, transactions is the number of transactions, the total transactions is the number of transactions a customer makes. So how would we interpret this? And there is the notes, but 320 should definitely know some interpretations right here. I'm going to untangle my cords. What would be the interpretation right here for total transactions? 320, you can totally help out 474 with this. This is really good 320 practice. And also, we have a thing right here that 320 also covered. 474 gets notes on this. We give them a big note set, and it's because it's kind of a review, but then I'm here to help. So we have, I'll start everyone out. 2 individuals, and then this is a multiple, who are otherwise identical. And I've got some good notes from today earlier on this. So let me kind of go back to that one. 2 individuals, because we're talking about people here, who are otherwise identical that differ in their blank by, and then we have to say 1 unit. We have to be careful here. 1 unit. 1 unit are expected to differ in their blank by blank units, where the person with the higher, nice job, Ellie, blank is expected to have a blanker blank. 2 otherwise identical individuals who differ by 1 in total transactions will. Be careful with the will. Change that to expected, because that sounds like cause and effect when we use will. Are expected to differ in their lifetime value by 165. The larger the number of total transactions, the larger we expect. So make sure to use words like expect in there because it's a prediction. But really, Ellie, that's worth 1,000 points of the week. Great job, Ellie. Just change it to expect and you're perfectly on track. And then make sure to say the units like you're saying because it's 1 transaction. So you want to change the units right here. Let me highlight this so everyone knows you're changing the units. But you want to make sure, yes, I wouldn't use should either. Oh, we will definitely do that, Jordan. You got it. We'll do a little forcing for then we're going to hop right to 201. You got it, Jordan. I wouldn't not use words like should. I would say expect or we predict or are likely. I wouldn't use are likely. We don't want to say this will happen or should happen because we're saying what we expect or predict. Does that make sense, Miles? Really good questions right there. We want to say things like two individuals who are otherwise identical. Now, this otherwise identical part comes into play 320 knows because what's going on with this? Why are we saying who are otherwise identical? Why is that so key here? 320 should know instantaneously because we've been covering this. We say otherwise identical because we're doing a blank type of regression. Because we're doing a multiple regression. Because we're doing a multiple. So because we're doing a multiple regression, we have to say 2 individuals who are otherwise identical, like they have everything else the same, but they differ, or you could say 2 individuals who are otherwise identical that differ in their blank. There's a lot of ways to change the wording a little bit, but make sure you have key components of this that you acknowledge they're otherwise identical. What else did we have? We could talk about that one real briefly. I'm not going to do gender male. Well, I basically have it right here. We did one of these earlier. And if you look right here, maybe I'll try to make it a little bit nicer. But right here, we have an interpretation from class earlier. You bet. We'll do more 474. You got it. 2 companies that, 2 people at this company who are otherwise identical, because it's a multiple regression, where one is, and I want to make this clear, this is the indicator. And this is the reference level. So this is an interpretation from 320 earlier today, but 2 people at this company who are otherwise identical, where one is male and the other is female. the person who is male is expected to make $458 more than the female. So if you notice, when we have a categorical variable right here, and I want to point this out, this is a categorical variable. This is a quantitative variable. So this one right here is quantitative. So this is quantitative. And this is categorical. So quantitative, categorical. So there's a different interpretation when we have categorical. You have to compare the indicator level to the reference level. Who's following me? 474, do you follow me that when you have a categorical variable, you will have different levels to it, and you have to compare the indicator level you're talking about to the reference level, and the coefficient right here is the coefficient in the model. That 458 is the coefficient in the model. This is the b right here, whatever this b of the ith variable, whatever it is, that is the coefficient right there. As opposed to with our previous model, which I'm going to take, it was 465. So by 165, I think, there it is. So this right here, this is the coefficient right here. That's the coefficient in the model. Yeah, so great question, Miles, right there, 100 points. The LM creates a linear model. LM stands for linear model. It's going to fit basically the mathematical equation. It's going to help us create a mathematical equation. Great question right there, Miles. And it looks like people are saying it makes sense. This is for your quantitative models, and that's the coefficient that goes in there. I kind of want to leave a little bit open-ended on this, but hopefully this sets people on the right track. You're welcome, Miles. Great question. And oh, we're over here. And here we are. So this one right here is the same deal. It just has multiple indicators. If you look at the output, you can see a whole bunch. But we learned this today in 320. What is the first level? Oh my gosh, I'm misspeaking. The one that is the first level is the reference level. So you see here, gender male is the indicator because female is the reference level. F0 to 30,000 is the income bracket level. And so here's all the indicators. These are all the indicators, and there are how many levels to income? How many levels are there to income? This is some easy 320 questions. This is great 320 review right now. How many levels are there to income? How many levels are there to income? There will be, I think, 6. There'll be 6 levels here, and I'll show you real quick. We're in value and income. There we go. 1, 2, 3, 4, 5, 6. And then how many indicators does this make? Miles, you get 1,000. Love all the answers, Miles. How many indicators will this create? How many indicator variables? Oh, no worries. How many indicator variables will these 6 levels create? How many indicators will it create? This is great 320 review. I want to put questions on the test just like this. How many indicators will this create? And we can see in the output. Oh, no, there's only 6. There's 6 levels right here. 1, 2, 3, 4, 5, 6. When someone responds, they'll say their income's between 0 to 30,000, 30 to 45,000, 45 to 60,000, 60 to 75,000. These are all like Group A, Group B, Group C, Group D, Group E, Group F. That's 6 groups, I believe. So there's 6 different groups someone can belong to when they say their income level. So how many indicators will this create? Since there's 6 levels, it'll create 5 indicators. That's because there's one that is reserved for the reference level. One becomes the reference level that all others are compared to. And so when you do the interpretations, key talk for 320, you have to compare to the reference level. You compare the indicator to the reference, and the coefficient is the difference between the indicator and the reference. You get it now? Does that make sense? You compare the indicator to the reference, and there's just one reference. I think, are you in the morning class? We talked about this already in the morning class. You get it now? Awesome. I think Amber wanted us to do question 4. So hopefully, Jake, is this making a good bit more sense right here? How's it looking, Jake? Pretty good. Hopefully. So let's go down to here. Oh, we're comparing models. Cool. I love comparing models. Awesome. So the one standard deviation rule. So when we compare models, what do? We're going to find what's between the models. So Amber and everyone, 474 and 201, you can help out with this. I love how everything has similarities right here with what we do. When we compare models, we need to take their differences and turn their differences into what? When we compare models, we need to take their differences and turn their differences into what? Take these models and look at their differences, but turn their differences into what? We could actually make a function for this. I'm going to make it a function for fun. So we want to take these models and we take their differences and do what? So we got, here's how good model A does. Here's how good model B does. Here's how good model C does. But then here's our uncertainty in it. It's like your friend says, I'll pay you $25.30, but it could be off by about $3.2. I'll pay you $29.10, but it could be off by $3.5. I'll pay you $31.90, but it could be off by about $2.2. So we want to take all of these estimates of what the truth is and compare them, but we need to turn their differences into what's? 201, how do we standardize differences? 320, how do we standardize differences? What term do we have to look at how far something is away from something else in terms of standard deviations? 1,000 points online. The larger the uncertainty, the worse it does. So these models, right? Well, this is just more uncertainty. The larger the error. So this is the estimate of the error right here. We're doing the estimated generalization error. So this model is estimated to do the worst. This model has the most uncertainty, but is estimated to do about average. This model is estimated to do the best, but has a medium amount of uncertainty. So this is saying, well, it could be 25, but we could be off by about 3. It could be 29, but we could be off by about 3.5. It could be 32, but we could be off by that estimate about 2. So how could we standardize these? How could we standardize these differences? How could we take the differences we observe and standardize them so we could compare and say, well, this is about how far the models are away. Like we could turn their differences into what? As in observation minus mean over standard deviation. We could turn, you just have to write one letter. Not average. So we want to compare them. We want to say, this is how far this one is away. This is how far this one is like from each other. And then let's divide by the standard deviation. We want to turn them into z-scores. So we're going to use the one standard deviation rule right here to see exactly, Jordan, 1,000 points right there, z-scores. Yeah, observation minus mean over standard deviation. You see 201, boom, to the rescue right there. Jordan worth 1,000 points, great answer. So we're going to turn them into z-scores. This is why I always say to people, a lot of what we do in 201, really carries through to later stuff. And this should be called Q4. And so let's write a function right here. All we're going to do is take, let's go first value. So we're going to take the first value minus the second value, and we're going to divide by the max of first standard deviation, second standard deviation. Okay. So I would usually write this out myself, but let's go here and go to return that value, first standard deviation, second standard deviation. Okay. So what I did right here is when we run this, I'll show you the first one by hand, then I'll use my function I created. We're going to take the first estimate, the second estimate, and I'm missing a parentheses right there. Then we're going to take, that one's missing a parentheses right there. Oh, it's because it went to the next line. There we go. And then we're going to take the first standard deviation for this one. And in truth, what are we actually doing right here? I mean, this is probably making it a little more complicated than we need. All we're doing is taking this difference up top and dividing it by the larger of the two standard deviations. So we're just dividing this difference up top right here by 3.5. It's going to solve that for me, though. So when I take the max of these two values, it's taking the larger of the two standard deviations. So I wrote a function up top here where I just call it, let's say, z-score models. Let's call it model z-scores. So with this model z-scores, all the model z-scores does is I can take this model here, the first one, it doesn't matter which order I put them in, and it's going to tell me if there's a difference. And the difference between these is a z-score of negative 0.8, which means this model and this model, which is the second and third model, their difference is less than 1 standard deviation. So are these models, are models B and C virtually identical? Are models B and C virtually identical? Their difference in terms of standard deviations is not even a full standard deviation. Are models B and C virtually identical? So if we draw it out on the normal curve, we would have expected their difference to be about here, because that's 0, no difference. But the model's difference was about here. So that's where they landed. They landed there on the curve. So these differences between the models are most likely by what? The differences between the model are within 1 standard deviation. Yeah. We haven't done... I think we're going to do one of those here in a moment. You got it, Dana. And feel free to ask a question on it. We did a lot of it yesterday, too. And so we'll do some of that. I think Jordan has the next question. It's a 201, so yeah. So the differences between these models look to be likely by random chance. Does that make sense, Ellie? Does it make sense what we're doing with this right here? We're taking the two models. We're going to compare their differences right here. And then we're going to standardize. And this is model 1, A and B being compared. And it has a difference a little larger than 1 standard deviation. We could compare model A and C right here. And I'm going to take the larger of the 2 standard deviations. So I should take this. And that's a big difference. So that's quite the difference between models A and C. And how do I compare models A and C? Well, I'm going to take the difference between the 2 estimates, and then I'm going to divide by the larger of the 2 standard deviations. Does that... I think hopefully that covers how to compare models to see if they're within 1 standard deviation of each other. Take their estimates. So here's estimate for model A. Yes, so there isn't a preference or one model between B and C. They are like, I think you're right, for B and C. Yeah, B and C are, there's no preference on B and C. Between B and C, the differences are so small that they're virtually identical. It's like you have 2 intervals and they're like this, and you're like, well, they overlap. But when they don't overlap, you're like, okay, now I should use this interval over here if it's the better one. So with models B and C, they're virtually identical. Now the one I did here, which I think was A and C, there is quite the difference. So on A and C, there would be a preference because there's a large degree of difference between the models when we standardize it. So you don't want to look at just the difference. You want to standardize the difference. You want to turn it into a z-score. So it's really just to view it visually here. All we're doing is model 1 minus model 2 over the standard deviation, and that just gives us a z-score. There you go. Yeah, great job, Ellie. And I love showing 201 especially that everything you're doing with z-scores, we do at the upper level too. It's like, okay, let's just look at the difference, divide by the standard deviation, and we should maybe put here max standard deviation, the max standard deviation, the larger one. And then once you do that, you've got it. Then you've figured it out. You've standardized the difference, and you can say, well, that's not that odd. It's within 1 standard deviation. Let's do it. Which one was... Jordan was asking about number 4 on the homework, right? And then Mohammed has one. I would love help on question 3 on chapter 14 homework. Is it chapter 14 homework? I thought I had it up. Where'd it go? Oh, here it is. Is it here? Here it is. Chapter 14 homework. Is it sampling distributions? I hate that there's 2 of these. Sampling distributions, Jordan, or is it confidence intervals? You were asking about 1.645. So is it confidence intervals or sampling distributions? And I didn't ask some questions. Which one? Is it this one right here? Which one is it? Is it this one? This might be one that Dana was wondering about too. Which one is it? Sampling distribution, that one is number 4. Oh, you want number 3, right? Cool. Is it the car one? I'll get a confirmation it's the car one, then we'll do the car one here. So with the car one, that's it? Okay, cool. Okay, so the first thing we want to do, great job, Dana, and Jordan's is a question for tonight's homework. And then Mohammed, we got some 320 coming up right after this. Feel free to drop your question in the chat, Mohammed, and we'll get started on it. Okay, let's take a look at this. We're going to grab this problem. We're going to head right over here. Jump in. There we go. Zoom in. I feel like it's gotten smaller in recent days. Maybe I'm just blinder. That's a problem. Carbon monoxide emissions for a certain kind of car vary with a mean. Okay, as soon as I hear mean, I'm going to go with my notation. You want to immediately start marking your numbers right here. If this is the mean, it is mu. If this is the standard deviation, it is sigma. And this is the sample size for which they're looking at it, it's n. Now here's the confusing thing. It does not say the mean for these 60 cars. It does not say the standard deviation for these 60 cars. If it was talking about for these 60 cars, it would be y bar and s. If it was talking about for a sample, we found a mean of this. For a sample, we found a standard deviation of this. This is talking about population. It's saying for a certain kind of car, so it's talking about the population. So that's why we use this notation right here of mu and sigma instead of y bar and s. Y bar and s are from a sample. They're asking what would happen in this sample. They're not saying they know the answers for the sample. So I think that's one of the confusing things about these problems is why are we using mu and sigma instead of y bar and s? It's because we're asking what happens in a sample when we know the truth for a population. So let's go ahead and take a look at that right here. Let y bar represent the mean CO2 levels for the company's fleet. Well, we need to check our conditions. One, are these randomly selected cars? Randomly selected cars. Yeah, we'll hop back to that here. We'll hop back to that in a little bit, Mackenzie. You got it. And then ask some questions about it. That's the tricky one, I think. That's the tough one. So we have right here, are these randomly selected cars? Probably. Are these cars less than 10% of all of these cars that exist? Definitely. I mean, I assume there's more than 600 of these cars unless they're like special edition DeLoreans. And then 3 is the distribution nearly normal. And we don't really have enough information to check that, but we know the condition that if it's normal, we only need a sample of 1. If it's skewed, it needs a sample of 25. If it's heavily skewed, it needs a sample of 100. That is the large enough N condition right there. And we're probably good. I wish it had us check it. It doesn't, but that's got that. So it didn't have us check the conditions. We'll assume we're good on them. Not the best of avenues, but we'll do it. Okay. So with this right here, we now need to draw the distribution. The distribution right here is going to be normally distributed if we meet all the conditions. That's what meeting the conditions means. With a mean of the mean and a standard deviation of sigma over the square root of n. And guess what? We've already figured this all out. Because all we need to do here is put in our numbers. The mean is going to be 3.031. The standard deviation is 0.8 divided by square root of 60. Square root of 60 is going to be about, brain is on 0.089, I say. Ah, my God. Is that right? No, that can't be right. 60 square root, copy, 0.8, divide by, I guess it is, 0.103. So now we know the mean and standard deviation. What are we going to do next? I need someone to tell me what to do that now we've solved for the mean and the standard deviation. What are we going to do now that we're going to solve for the mean and standard deviation? Someone help me out. Once you know the mean and standard deviation, you should instantaneously think, I can do this right away. Hey, look, we haven't really looked at the questions yet because we're just taking the steps to do what we need to do. Because we're checking the conditions, which we should do for this chapter. We should always check the conditions, and then we should figure out the mean and the standard deviation, and then what should we do next? Where should we go, or what should we do? I'm prepared in 2 ways. There's 2 options I have right now. Both are fine options. Whether I want to do it online or by hand. So who knows, 201. What should I do now that I know the mean and the standard deviation? This found the mean and the standard deviation for the distribution. So what should I do? I need an idea. We know the mean, we know the standard deviation. David M. Lane, Jordan, you're right. You could also draw it out. Another fine answer would be draw it. We're going to go easy today. We're going David M. Lane. Nothing wrong with going to David M. Lane. Boom, David M. Lane. I think the mean was 3.031. Was that it? Let me double check. Great job, Jordan, right there. 3.031, and I'm going to copy paste. I carry all the decimals till the end when I go to the applet. So there we are with the David M. Lane. And so here it is. Sometimes when you put so many decimals, it gets mad. Sure. Get mad, applet. Okay, get really mad. But it doesn't show the last number, which I really dislike, but we'll take it. So we're going to go ahead and screenshot this right here. I'm going to go and put a lower number, or there we go. I just want it to not be shaded. Okay, cool. So one, we can go to David M. Lane and get the answers pretty quickly on this, but let's go ahead and look over the questions and think through this for a moment right here. There we go. So all we're doing is letting David M. Lane draw this for us. We could put in that last standard deviation if we want. It's going to go up to 3. I don't know why Applet still does this to this day. And that's going to be... My brain is just slowing down today. There we go. That's pretty close. Should be about what's that. 3.341. So one of the questions asks, the first question asks, what will the distribution look like? Will it be normally distributed? That's what we did first. We said it'd be normal with a mean of 3.031 and a standard deviation of 1.103. There we go. And then it wants to know between 3.1 and 3.3. So 3.1 is going to be right here. And 3.3 is going to be right about here. So I think that's about at 25% above there. And that's about 1% above here. You're not meant to know these things. Or no, that's like 0.5%. That's a very tiny small amount. That's about 0.5%. Okay, so about 24%. 24%. Let's take a guess right here. This is just a guess. You don't guess. Don't worry about guessing like this. So, we get 2 guesses. I said 24, right? Nope. Okay, so 3.1 to 3.3. So we go here, and we go between 3.1 to 3.3. If you look, this should look similar to what I drew. Let's look at our drawing right here. I'll shade it in. But if you look at our drawing, should look very similar. This is when you have practiced and you know you have it down. You want to try to draw what's on there without it doing it. So try to do this. Always try to draw it. And you see we have a pretty good drawing. I said about 24%. It was 24.7. I should have went with 25. But I was pretty close in my guess. Sometimes I get the guess. Sometimes I don't. But it was 24.7. So we were very close, and we had a good estimate for what it was. You don't have to estimate as well as I do, but you should, be able to shade it. If you can shade it, you're doing fine. And then we should be able to tell that it's way less than half of the curve. Because sometimes we'll put an answer on the test, and we might put like 20%, 80%, and it's like, okay, this is a smaller portion of the curve. This last question right here wants the top 1%, I believe. And the top 1% is going to be right about there. We'll go to the top 1%. There it is right there. And so it might round up to 3.3. It does. So the top 1% is going to round up to 3.3. And please note, I clicked over to this button to talk about the top 1%. And it's going to round up to 3.3. Does it want the top 1% to say? Top 1%. 3.3. Is this making more sense, Jordan? Does that make sense how to do this one here with the applet? And Dana, did you have another question on these? I'm more than happy to do another one right here on this. Is there another one of these problems that you currently are working on? Like be like, oh, the waist size one or the simulation one. Awesome, Jordan. The biggest thing is getting the numbers into the applet. If you get this one right here with the mean and standard deviation right, then you should be able to do the between two numbers. And you should be able to do the top percent. Also knowing that with the top percent, clicking this button right here and putting the area and doing this, that's the top 1%. Check the visual to make sure the visual's correct. That's why a lot of times you'll see me drawing the pictures over here. When I talk about where the top 1% will be at, I'll do something like, okay, the top 1% is going to be right over here. That's where the top 1% is. And so I would have had a hard time guessing. I'd be like, it's about 3.3. It's about 3.3 when it rounds up, because you're going to round up for it. But that's got it. Let's see if anyone has any other 201 questions. We'll do another 201, and then we'll do 320. Mohammed, which 320 were you wondering about, Mohammed? Feel free to drop. Did Mohammed say which one? And then Miles, did you have a question on 320? Let's see. Question 1 for 320, Mohammed says. I see question 1 for 320, Mohammed says. Could you do 4? I thought I was doing right, but yeah, let's do number 4. And then I think we'll hop to some 320 here. Great job. So glad to see so many people here. Just hang out, ask your question, drop in the chat, and I'll make sure I because I review the chat and everything. So with this one, great job, Miles. Excellent work. So this question right here, it's going off of the formulas we just used. The formulas we just used were, let's go open a new page. The formulas we just used is that the distribution of the sample mean will be normally distributed with a mean and a standard deviation, which is sigma over the square root of n. So when you look at this right here, the mean is always going to be the mean. So whenever we do the sampling distribution of the sample mean, the mean is the mean. So ignore the data right here. This is a simulation. This is a simulation which has nothing to do with these answers right here. This is a simulation. What is the mean right now? What is the mean for my data for 1,004 men? What is the actual mean of these 1,004 men? What is the actual mean for these 1,004 men? What is the actual mean? So what is the actual mean for these 1,004 men? Remember, this is a simulation. This is not what we actually observe. It's just a simulation. So what is the actual mean? Exactly. So if I were to take a sample of 2, then according to the calculations right here, the mean should be the mean, and the mean should just be that. So there's the mean at 2. What's the mean at 5? Well, the formula is consistently the mean is the mean. This is the portion of the formula I'm using right now that says that the mean for the distribution of the sample mean is equal to the mean. So it's always 36.24. That's what we would expect. And it's going to be that no matter what the sample size is. Don't worry about the simulation. This is just like a hypothetical scenario over here. The mean is the mean no matter what the sample size is. But what changes as the sample size gets larger? As the sample size gets larger, what changes? Great job, Jordan, right there. Yep. So what changes as the sample size gets larger? As the sample size gets larger, I didn't like that mu. As the sample size gets larger, what changes? Which portion of this equation changes as the sample size increases? The standard deviation, exactly. And it gets smaller by a factor of the square root of n. So as we see right here, if we were to put in here 2, we're going to say that the standard deviation is going to get smaller by a factor of square root of 2. And we're just going to increase n every time we compute this. Now, it's important to know, once again, this is a simulation. These are not the standard deviations. This is what we observe in a simulation. We have over here 3.94. So let's go and take 3.94 and divide by the square root of 2. So square root of 2 and 3.94, divide by it, 2.79. Now we take 3.94. Well, we have to do square root of 5 first. And then 3.94 divide by that, 1.76. And now we do square root of 10. And 3.94 divide by that, what is that? I think I got a mistake right there. Oh my gosh. I saw the next numbers. There we go. And then we take square root of 20. And we go 3.94, divide by that, and we get 0.88. And your answer should be kind of close to the numbers on the right. If you notice, 2.79 is the answer here, 2.79, 1.74, 1.76, 1.26, 1.26, 1.87, 1.88. Your answer is, oh, what did I get wrong? What did I get wrong? Who caught a typo in there? Let's double check. 20. I have a typo. Oh my gosh. I haven't gotten one wrong in a while. 2 decimal places. Oh my god. Really? Ah. Oh, it's that easy to make a mistake. It's that easy to be off by decimals. Just double check your answers. Be very careful. We're all capable of mistakes. It happens. Just off by 1/100th. And yup. Tell me if that happens to you. I'll correct it. I made the mistake, so you get that correction if it happens to you. So if you look, the numbers are very close to the simulation. So the simulation and the theoretical values are very close. This is according to theory what we should see, and this is when we simulate what we should see. And the simulation or the theoretical values are supported by the simulation, so they're very close. Now, when we look at the simulation histograms, what do we see? The histogram starts out left skew, but as we increase the amount we're sampling for the mean, the histogram becomes more blank and more blank. So as we increase, the histogram becomes more blanker and more blanker. This is the central limit theorem right here. According to the central limit theorem, as we increase the sample size for the distribution of the sample mean, the distribution will become more blanker and more blanker. What will it become? One of the two things. I need one of the two things. It's going to become more, and it's going to become more like that. What two things will it become? More unimodal, more. It's going to become tighter and more normal. So if you notice right here, it spans from 30 to 42. Or up here, it spans from 26 to 46. And here, it's only not even going from 32 to 40. It's going to be tighter and more normal. And so this part of it is the more normal part because eventually it will be described by the normal. So eventually it will be described by the normal. And this is the tighter part of it. The tighter part of it is due to the over square root of n part, because as n gets larger, the standard deviation becomes smaller. So since we're doing sigma over the square root of n, it gets tighter. And then eventually, if we meet all the conditions, we have a large enough sample size, it will be normally distributed because it's going to eventually be well described by the normal curve. Does that make sense, Jordan? There's the two things to the central limit theorem that becomes tighter and more normal. And when does this work? Truthfully, I think it works at about 10, but I've done this problem enough that it's going to work at 5. Yep. I think it works at 10, but they say 5. Not today, my Pearson. You got me on the other one, but not today on this one. The distribution of the original data is pretty normal. If you look here, we see uniform. Uniform means flat, like a bread box. Bimodal means it's got 2 bumps. And so it's definitely not unimodal. It's definitely not bimodal. The only choices here are nearly unimodal and symmetric. So it does not take a large sample size to do it. It's going to take a very small sample size. Does that make sense here, Jordan? We're going to do question 1, 320, I believe, here in a second. Question 1, 320. Add in those questions if you got them. So many tabs. People usually look at my computer and they're like, how do you have so many tabs open? And like, I don't know. I have 4,000 tabs. See, I say that and then no one will believe me. I could say I had 50 tabs. And well, no, I don't have 50 tabs. This one is worth 2 grades. It's due on Thursday. So make sure to be working on the assignment. Let's see, how's chat doing? You're welcome, Jordan. Great job. Great job. Let's hop in here. Okay. So with question 1 right here, we're going to use the auto data set. We've discussed this data set. Make a scatterplot of the variables in the data frame. Do the relationships of each predictors with fuel efficiency look linear? Do they look linear? So we need to see if there is a linear relationship between all these. I think this is the right assignment, right? Yeah, we didn't do polynomial fits last time. Cool. So we're going to see if there's a linear relationship with the scatterplot matrix. So just let me double check here. Yeah, scatterplot matrix. Cool. Okay. So let's go here to pairs. No, go away. The function is pairs. And I think we can just do, are we doing the X4 bikes? No, we're doing, what's the data set called? Auto. Okay, so we need to load in data auto. So there's the data auto. And there we go. And here it is. See if we have the variables in the right spot. Oh my gosh. Okay. Come back. Plots. Okay. So here it is. That's better. Cool. So we have here the relationship between, and you know what? Because we're doing fuel efficiency, right? Okay, so we need to fix this. So fuel efficiency tilde dot comma data equals auto. Fuel efficiency not found because I can't spell. There we go. Okay. So the reason I switched that is because I want that in the Y position. I want that to be in the first kind of column right here. And which of these looks to have the greatest problem with linearity? Which of these looks to have the greatest problem with linearity? Which of these looks to have the greatest problem with linearity? Do any of them look to have linearity problems? And we could use our package from last week. While you're thinking that over and looking over these right here, we used a package last week. It was the psych package. And I can't remember the function we used. Oh, it's got a billion things. Oh, no. What was that function we used? Could you touch on question 2 for 30? Yeah. Were you wondering about this one right here, Mohammed? This is your request. Is it pairwise plot? Might be pairwise plot. What's that? I don't know that function we used. I'll have to look it up again. But when you're looking at the linearity between the y variable and the x's, you want to look to see if a line would go through this data. So I don't want to answer it fully. I want you to think it over a little bit. Does a line look like it well describes fuel efficiency and horsepower? Does a line look like it well describes fuel efficiency and top speed? Does a line look like it well describes weight? This is weight right behind me right here. Weight and fuel efficiency. Which of these looks to be the least linear? So what we want to do now is we actually want to fit the full model and examine the summary with the check regression, and let's see if there's issues. So let's do that real quick here. So we're just going to take our model that we have. We're just going to go here, and we're going to put it in. There we go. And do a summary. There's a few of them. There's definitely problems in here. Like, overall, yeah, I think, is it cab volume? I'm least concerned. Cab volume. Do you see this right here? Does this make sense, Miles? Do you see that? We're looking for issues of linearity, and that's a pretty big bend in the model. That's a big non-linear. Because if you fit a line through this, the line's not going to fit well. So this has outliers. This is weird over here, but it's kind of linear through that. And it's not linear at the end, but that's like an outlier. This one looks to have the most non-linear, kind of non-linear, probably pretty linear right there because the line goes through it. This one is kind of weird, maybe some non-linearity, but my greatest concern is here and here. I can really see there's a strong non-linear relationship. So we look at, yeah, great job, Miles, right there, 100 points. Yeah, that's what we want to look for with this, is we want to say, does a line well describe the data? Is it linear? And I see the bend there, not really a bend, and outlier, maybe some linear relationship. So I'm most concerned about horsepower and top speed. When we check this model right here, let's take a check of it. And what do we see? Wow, look at this. Which ones do we see the issues with? We see the issues with horsepower, top speed, and weight. So horsepower, top speed, and weight, which are in here, horsepower, top speed, and weight. We'll try to make it big enough so we can kind of see those plots. But here's the horsepower, top speed, and weight. Even weight has a nonlinear component to it. So this one right here that I thought looked good actually has some sort of nonlinear component to it. The only one that is good is cab volume. Cab volume is good. The linearity of the overall model is good, which we see in this plot right here. That doesn't have linearity issues. The normality says it's a problem, but are you really concerned about the normality of the residuals? The normality of the residuals looks to probably have issues because of this, which are these two high outliers right here, and maybe down here. Oh, that outlier is actually good. It's on the, you can barely see it. It's right there. So that outlier, you can barely see above my mic. It's this one down. It's not even outlier. It's actually where we would expect it to be, oddly enough. So the real issue are these 2 points, which are up here. And you can see them right here. They break away from what we would expect according to the normal model. So overall, I don't think normality is an issue. Even though we fail it, I'm like, nah. I don't think equal spread's an issue. I guess it's freaking out because of these. It says that equal spread is bad, but nah. The real issue right here, and we'll go to the extra equals true. The real issue right here, is it extra? Yeah. The real issue is going to be these plots. And you really see it right here. Let's bring these over. Yeah, you can see it in all of them now, except for the first. When you look at these plots right here, you really see the bends away from the linearity. Because if you draw how the data actually goes through it, you get something like this, a little bit of that, and I guess this one, just that. So other than that outlier, there's not really a problem with these. The problems look to be in horsepower, top speed, and weight has a problem too. Maybe weight, now that I look at it, there's the bend up at the end there. So trying to draw, like, how is the model actually going through it if it goes through the center of it? Because remember that this line right here, this line going through the middle of the data is meant to be at the middle of it at all times. It shouldn't, the data points should be equal on both sides of it. Above and below it, there should be equal amounts of data. But you notice right here, especially, let me highlight a real big point. If we go to a like major problem area, you'd go to right here and there's only points above. That's not good. And then you don't want to see like only points below. You want to see points equally distributed for the linearity condition to be met. So that's the issues. And yeah, that looks pretty bad. We can do, there's one I want to do right here, and then we'll do number 2. So we need to choose the order for these models. So when we choose the orders, we need to figure out how to do choosing the orders. Yep. So let's go here to model LM and fuel efficiency tilde cab volume. So I'll do the first one right here, cap volume. And data equals auto. Cool. And then let's go to choose order. Okay. Need someone to help me here. 320 help me. So 320 help me with this. How do I use the choose order? How do I do choose order? How in the world do I work with this output right here? We reviewed this a lot. So how do I work with this output? This is actually the easiest one. But how do I work with this output? Step 1, do what? Step 1, do what right here? What do we do for step 1? Any ideas? Choose the what first. What do we do for step 1? No. How do we choose the order? Step 1 is to find the what first. When you get this output, what do you do when you get this output? These are the 3 steps to find the right order using choose order output. Step 1 is to do what? I'll tell you all the rest of the steps. I just want someone to tell me step 1 or take a guess at it. What do we do when we get this output to find the best order? No. See, in class, I would just look at people and I'd be like, okay, who's going to answer? I don't know how many people are watching right now. What do we do? Muhammad or Miles, are you here and do you know? So get Miles, 1,000 points. Thank you for taking the guess right there. The first thing we'll do is we'll find the highest R-squared adjusted. So step 1, find the highest R-squared adjusted. So we find the highest R-squared adjusted here first. And so that is our starting point. Now you can only consider these models. These are the only models. Once you find your highest R-squared adjusted, and you see how I found this? This is simply the highest. So once we find the highest R-squared adjusted, we then consider all models that are it or lower as possible models, because we're going to take that one or a simpler model. Because we're saying, okay, this is the best, but I'm willing to take something that's simpler if it works just as good, basically. We take this, and then we subtract 0.005 off of it. So we subtract 0.005 off of it, and then we start with the lowest one, which is the line, and we say, okay, is this good? Does this meet this standard right here, Miles? Is this higher than this? Yes or no? So we're asking, is this value right here higher than this? Is this value right here higher than this? We're on to step 3. Step 1 was find this. Step 2 is subtract, and then you're right, Miles, this is not higher, which is step 3. So we're going to continue. Is this higher? Yes or no? Is this value higher than this? Yes or no? Is this value right here higher than that value? And once again, the answer will be no. And then we get to this one, and this one is higher. So guess what? The answer for cab volume, which I think was right here, is going to be third order. So we're going to use order 3, the third order right there, because that does meet the criteria. So this is what we'll do. We'll fit the third order model, the third order polynomial rather. And so does that help out with that, Miles? The steps right there, the 3 steps. 1, find the highest R-squared adjusted. 2, subtract 0.005 from it and use that as your standard. 3, start with the lowest one and check to see if it meets the standard. And if it doesn't, keep checking until you get the first one that does. Do not start down here. Start with the lowest because we're trying to get a simpler model. The goal is to get the simplest model that basically works as well as the best model. So this model right here was the one we chose originally, and that's the one we're going to use. But we checked these models to see if they work just as good. So that's got it. Nice job, Miles. Where is question 2? Question number 2, fit demand predicting from all the variables. Examine the influence plot for this model. Cool. So we're going to fit demand from all the variables. And let's look at the influence plot. Demand tilde dot at dot. Data equals EX4 bike. And here we go. Let's look at the influence plot. Wow, holy mackeroli. So we have a point right here that is extremely influential. We have a point that is through the roof. Crazy influence right here. Now, where is this point? It's 0.337. 0.337 has crazy undue influence on our model. So what does it ask us right here? There is one extremely, you bet there's one extremely influential point in the data set. Show the influential row and then explain what makes it so unusual. Through the scatterplot matrix, it's not possible to see why it's unusual with summary on the individual variables. So I did this earlier today, and we can easily get this right here. And I'll drop this in the code now. So we can bring the pairs right here, but we're going to do something cool. I thought this was magic when I first saw it, but you can go PCH and change the point style. And so I guess 40 exists. Whoa, oh, I think it just says 40 everywhere. You can go CEX and change the point size. So now they're a size 2. And you can go col and you can change the color to something like red. But we're not going to stop there. What we're going to do is we're going to use an if-else. So 474, listen up. If-else. If the row names of EX4 bike is equal to 337, then the PCH, oh, we're outside of it, then the PCH will be equal to, and this is point style, 16 if not 20. And let's grab the if else, drop it right here, drop it right here, and let's go here and change this to red. Let's go here and change this to green. Did that to me earlier today too. And this changes the point size. Let's go here and make this 1.2. Let's make this 0.2. Run it. There we go. That's got it. And so we get a bit of an interesting plot right here. It's like Christmas, but reverse Christmas this time. So you can see the unusual point in all the plots. The unusual point is row 337, and we've made it really stand out by making it bigger and making it different point style. And it looks like to me that it has unusual combinations of its average temp and effective average temp. So you can look at the summary and see where it's low. So you can see when you look at the row itself that its average temp is a little low. Its average temp, let's get it all on the screen one time. Its average temp is 12.2, which is in the lower 25%. Its average temp is in the upper 25%. Its effective average temp is in the lower 25%. So it's some sort of combination of these two, which is giving it a weird bivariate combination. Now, this weird bivariate combination of the x's is leading to its strong what? The weird bivariate combination is leading to its what? The weird bivariate combination of its x's is leading to its large amount of leverage. And then the model doesn't do well at predicting it, which leads to its large deleted studentized residual. So you have a two-factor thing. You have its its really weird combination of x's that leads to its leverage, and you have the model not predicting it so well, which leads to its large deleted studentized residual. And you see here the two scales, the leverage, which is behind me. And I'm going to handle the last question right here. Why don't I? There we go. Here's the leverage right here. And that's the weird combination of the x's. And here's the deleted studentized residual, which is the model not predicting it so well. And so there was a question also about let's go back to the 474. Where's that output at? This one right here, where is it? Here it is. So I don't want to give the full interpretation, but if you're 474 and you're still here and you're wondering about how to interpret that last one, these are all indicators. These are all indicator variables, and they will all be compared to the reference level. So when we have this income level right here, we will compare this income level, because this is an indicator. Here it is right here. We will compare it to the reference. So this is the difference right here. This is the coefficient for the difference. Can you explain Q from Salient distribution how the... I think we might have done that one earlier. Audrey, are you talking about the CO2 one? Is that the CO2 one? If it is, I think we did that one just a little bit. Yeah. Rewind. You can actually rewind the video live, and you should see me going through, and we did that one right here. So we were going through and working this one right here. It should be about 20 minutes into the video, I think. So you'll see me working this problem right here. And the coolest thing about YouTube is you can like rewind live. You can't ask questions on the one. Oh, you're welcome. And if you're stuck, ask away. And we did this one yesterday too, so you can see two works of it. But yeah, great questions, everybody. Great job. And so the last thing I want to point out right here is, where's the interpretation right here? So when you interpret indicators, what is that 22, the difference for salary? No, it's for customer lifetime value. So it's for customer lifetime value. So this would be two customers who are otherwise identical, but differ in their blank, their income level, where one is a blank and the other is a blank. So if you see, this is an interpretation, but not for this problem, but for our problem, it'd be two customers who are otherwise identical, because we're doing a multiple regression. We don't put that part, but two customers who are otherwise identical, but one has a blank of blank and the other has a blank of blank. We would expect their difference to be blank, where the blank has higher. We would expect the blank to have a higher blank. But I guess since it's negative, you might just say we would expect the blank to have a lower blank. Does that make sense, Mackenzie? This is the interpretation that's key right here. You'll always compare the indicator to the reference level. And so make sure you know where your indicator is and make sure you know where your reference is. Is this making more sense right here? How's it looking on this? How's it looking, Mackenzie? And then here's the coefficient right here. The coefficient, and then make sure it sounds like it should sound. Good, awesome. And you can send it to me if you want me to check it. Send it to me via email or Discord, and I'll look it over and I'll be like, yeah, that's good, or change these things. Use words like expect. Don't use words like will. A lot of people use like they will differ by this. No, don't use will. Well, excellent office hours, everybody. Wow, we did 201, 324, 74. I'm just gonna take a stretch. I'm just gonna stretch and relax. We got so much good work done. So any other last questions? 201 has an assignment. 320, 474. So much. We only have 3 more weeks. 3 more weeks, and this will be the last office hours. I can't believe it. You sent it on Discord? Awesome. Let me see. I'm going to kind of mumble it. Okay, wait. Here we go. Let me see. Oh, wait. That's the wrong one. Is it? No, wait. That's the wrong one, too. But wait. Did you send it? Wait. Here we go. Okay, here we go. Good. It was right. Oh, and then to the other one, it's going to be the holdout, Mackenzie. Only focusing on the holdout. The holdout is when overfitting occurs. So you're welcome, Miles. Great work. And so Mackenzie, for the other one on Discord, with the graphic, models start overfitting when they do worse on the holdout. So when does it start to do worse on the holdout? So models start to overfit when they do worse on the holdout. Does that make sense? Like that's as big of a hint as it could possibly get. The model starts to overfit at the point which it starts to do worse on the holdout. As when you add new variables, it's taken too much information and it starts to do worse on the holdout. So that should point to that one. Let me read over the thing right here. Just the very end of it, the one who is making 30 to 45,000 is expected, and then compare them, is expected to have a lifetime value that is blank less or more than the other person. Does that make sense? Because that's why it's called the reference, is because you're going to compare them. If you just want to do that small revision, that's where the problem is at the end, because it's going to be, we expect them to have a lifetime value that is blank compared to the other person, because that's why the other person's the reference. If you see here at the end, the person who is male is expected to make this much more than the person who is female. So you still do the comparison here at the end where you say the person who is this is expected to have this much more. So you're going to compare where you have two otherwise identical individuals where one is the indicator, one is the reference. The person who is the indicator is expected to make this much more than the reference, or just depending on the context. Does that make sense, Mackenzie, right there? I think hopefully that someone else sent me some code on Discord, but how's that looking right there? So make sure at the end to do the comparison. It's awesome. Great work. Great work. So I love it. I love if you can send like messages, like if it's like an answer. But great work. Send me some more messages. We'll be looking over stuff. Go out and vote. I think I've told, how many times has Brian said go out and vote? I hope I've said it 100 times, because that would mean I've said it almost enough. Anyways, go out and vote. Tell your friends and family to vote. With that, I'll be back. I'll be teaching in a little bit. Send me your questions if you have them. I'll talk to you later, everybody. Bye.
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam.
No!